Hello everyone, it's me again, Ma'am Sheila. In this video, I am going to discuss all about the photoelectric effect. But before we proceed, let me ask you something. Is light a particle or a wave? To answer that question, truthfully light exhibits a dual nature. It behaves both as a wave and a particle, where it is known as wave-particle duality. It displays wave-like properties like diffraction and interference. Simultaneously, light also behaves as a stream of particles called photons, where each photon carries a discrete amount of energy that is demonstrated by the photoelectric effect, where light interacts with matter in discrete packets rather than as a continuous wave. Imagine light is made of tiny packets of energy like little marbles. These marbles are called photons. Each photon carries a specific amount of energy. The amount of energy a photon has depends on its frequency. Higher frequency light has photons with more energy than lower frequency light. This relationship is described by the equation E equals hv or E equals hf, where E is the energy of the photon, V or F is the frequency, and H is the Planck's constant. Photons are always moving, and in empty space, they all travel at the same incredibly fast speed, or the speed of light, where c is equals to 3 times 10 raised to 8 meters per second. Photons also have momentum. Momentum is a measure of how difficult it is to stop something that's moving. This relates to the frequency and wavelength of the electromagnetic wave as expressed by the equation E equals hf and P equals h over lambda. In 1905, Albert Einstein explained the photoelectric effect, demonstrating that light energy is quantized, and showed that when ultraviolet light hits a metal, photons can collide with individual electrons, transferring their energy. For this process to occur, the light must have a frequency above a certain threshold specific to the metal. Einstein formulated the photoelectric law, restating the law of conservation of energy. This law states that the minimum energy required to free electrons from a metal is known as the work function. The work function can be calculated using the equation work function is equals to Planck's constant times threshold frequency. Planck's constant is 6.626 times 10 raised to negative 34 joules second, or 4.14 times 10 raised to negative 15 electron volts second. The value 6.626 times 10 raised to negative 34 joules second represents Planck's constant in joules seconds, which is a common unit system in physics, and the value of 4.14 times 10 raised to negative 15 electron volt seconds represent the same fundamental constant but expressed in electron volt seconds. When a photon strikes a metal surface and releases an electron, any remaining energy from the photon is converted into kinetic energy. The maximum kinetic energy of the photoelectron can be expressed as Kmax is equals to 1/2 mv max. The energy of the photon can also be calculated using the formula E equals hv or E equals hc over lambda, where c is the speed of light that is expressed as 3 times 10 raised to 8 meters per second, and the lambda is the wavelength of the light. Let's have a sample problem. A piece of lithium metal has a work function of 2.93 electron volt. Determine if the photoelectric effect will occur when illuminated by green light that has a wavelength of 550 nanometer and ultraviolet light that has a wavelength of 200 nanometer. If the photoelectric effect occurs, calculate the maximum kinetic energy and maximum speed of the emitted photoelectrons. Let us first calculate the green light. So for the green light, we use this formula. Energy is equals to Planck's constant times the speed of light divided by the wavelength. So 4.14 times 10 raised to negative 15 electron volts second times 3 times 10 raised to 8 meter per second over 550 times 10 raised to negative 4 meter. So we will cancel this out, and the nanometer will be converted into meters. So by that, we will have 2.25 electron volts. So in the green light, the photoelectric effect will not occur since the work function of the lithium metal is 2.93 electron volts. Let's now proceed to the ultraviolet light that has a wavelength of 200 nanometers. So for the ultraviolet light, we use this formula. Energy is equals to Planck's constant times the speed of light divided by the wavelength. So 4.14 times 10 raised to negative 15 electron volt seconds times 3 times 10 raised to 8 meter per second over 200 times 10 raised to negative 9 meters. So the nanometers were converted in meters. So we will have 6.21 electron volts. So since the lithium metal has a work function of 2.93 electron volts, the photoelectric effect will occur in the ultraviolet light. So because of that, we will find its maximum kinetic energy and its maximum speed. Let's now proceed in calculating the maximum kinetic energy of the ultraviolet light. So this is the maximum kinetic energy of the ultraviolet light, which is 3.28 electron volts. Let's now proceed in calculating the maximum speed of the ultraviolet light. So, this is the maximum speed of the ultraviolet light, which is 1.07 times 10 raised to 6 meter per second. So, that would be all for our problem solving number 1. Now, it's your turn to explore further. Try solving this practice problem and let me know in the comments how you get on. And with that, we've successfully navigated the sometimes confusing but always exciting world of the photoelectric effect. Hopefully, you're now a little less confused and a lot more enlightened about the behavior of light and electrons. Thank you for watching, and remember, physics can be fun. See ya!